Okay, so hello everyone. My name is Andrea Muciaccia, and I am a PhD student in Politecnico di Milano as part of the Compass Group. And the work that I will present today is basically what we are carrying out in Politecnico, also with Demos UK and the European Space Agency. So what we are doing is we are developing a tool that is STM, whose main goal is to, let's say, to track the health of our space environment. And let's say that we have two ways. One is to assess the impact of a single mission on our space environment, so how they affect the population of objects already in orbit, and also to assess which is our overall capacity of our environment. And this because we have to think of the space as a resource that is of finite capacity. So we have also to assess which is the maximum capacity that we can have with our missions. So today we will just focus on the first goal, and we will see some results in terms of fragmentation effects on the population of active objects, and also on the application of this of the index that we are developing on the on a set of objects. So before going to the results, a quick overview of our model. So what we are building is a risk matrix in terms of probability and severity in terms of collision and explosion. And basically, we compute our index along the entire lifetime of our mission. So we will have the computation of the index during a generic phase that could be an operational phase, an orbit injection phase, or a transfer phase. And then we will have a contribution related to the post-mission disposal, accounting also for possible let's say, fail end of life. In case our end of life is not good, we can also have this accounted in our formulation through a reliability parameter alpha. So more in detail, at each epoch of our mission, we will have two terms. So one term related to the collision, so one collision probability times the severity of this collision probability, and one term related to the explosion probability and the related effects. So the collision probability is modeled through a flux-based model, and the information about the debris flux and impact velocity are extracted from the ESA master rate tool. And in this way, we can build some maps in terms of flux and impact velocity, and then we can compute the collision probability with the objects that we are analyzing. Then we have the explosion probability that instead is based on historical data, and these data are gathered from the ESA DISCOS database. And from this historical data, we can compute the, let's say, the survival rate with this Kaplan-Meier estimator. And this will be done according to some classes or families of objects. So we will have rocket bodies, payloads, but also subclasses in terms of the rocket bodies, like possible families of rocket bodies. So then we have the last terms, which is the effect term, which is the most complex term of our formulation. And this accounts for the effect of possible fragmentation in the space environment on the population of the active objects that we are studying. So basically, we define some reference objects inside our population. Then we generate some fragmentation, and using a density-based model, we can compute the cumulative collision probability between the fragmentation that we generated and our reference targets. And in this way, we have an idea of the effect of possible fragmentation on our population. So we can generate maps in terms of effects, where the peak represents the region in which, if we have a fragmentation, we will have a higher possible effect on the population that we are studying. So more in detail, we for the population of objects that we study, we just select the active objects, and we retrieve the information in terms of location and physical properties from the, again, the ESA DISCOS database. We define these reference objects according to the cross-sectional area of the objects on a grid that is defined in Keplerian orbital elements according to the orbital regions that we are studying. And in this case, the plot on the right refers to the lower orbit region, for which we are considering the semi-major axis and the inclination as study parameters. So then once we define this, let's say these reference objects, we generate in each bin of the grid a fragmentation that could be either an explosion or a collision. And then we propagate the fragments generated using a continuum cloud approach. Then with these fragments generated, we evaluate the collision cumulative probability, the cumulative collision probability between the fragments and the targets that we have defined. In this way, we build these maps in which we have accounted for the effects of possible fragmentation. So now we can go to our first objective of this work, which was the study of these fragmentation maps by looking at their evolution when we introduce large oscillation. So the first goal was to investigate the influence of this large oscillation on the population of objects. And to do so, we started from an initial population where we removed all the objects related to large oscillation, and then we inserted, let's say, a dummy large oscillation in the population that we were studying in order to see how they influence our space in terms of effect of fragmentation. So the first study was to just introduce one large constellation and see the effect in terms of deployment of the constellation, while the second study was mainly related to the location of the constellation. So to see how the effect of this large constellation change if we place the constellation in another location in terms of semi-major axis and inclination. And let's say that the main results will be shown in terms of representative objects that we select, the location of the peak, but also the value of the peak in terms of effects. So starting from the deployment of the constellation, on the left, we have the effect maps that I previously introduced. And what we can see is that when we place this constellation that has more or less the same location of the OneWeb constellation, but different physical properties, when we introduce the constellation, we have that the white dots that are our reference targets, they change. So some of targets are removed because of the introduction of a night mass and a night area in terms of location for the constellation. And moreover, we can see the appearance of a third vertical band in the effect maps. And this indicates that that deployment of this constellation is generating a region where possible fragmentation can have an effect. In this case, the main peak is in the location of the constellation, but as we will also see in the following slide, this can be, let's say, a special case because in this case, the constellation is at about 90 degrees in terms of inclination. Indeed, if we change the location of our constellation, we can see that the peak is moving both in terms of semi-major axis and inclination, but also in terms of peak value. And this because this effect is mainly related on the distribution of the flux of the generated debris and also on their location, because if they are at lower altitude, they will re-enter or they will burn in the atmosphere. So what we will have is that the peak value will be, let's say, guided according to the location of our constellation. So then we have our second goal, which was the application of our tool to a set of objects. So we selected all the objects that we had on orbit, and we added our constellation. So the first one that I showed in the previous slides. And we wanted to compute our index to all the objects for during the deployment of the constellation. In order to have like a feedback effect on the constellation itself, we also changed the effect maps in the computation for every year of our analysis. So the results shown that if we place our satellite in a semi-major axis and inclination grid, and the marker size represents the, let's say, the level of the index associated to each mission, we can see how the introduction of the constellation will overcome the index of, let's say, the severity of all the other objects. So at the beginning, we have that the most crowded region is the one in sun-synchronous at lower altitude, more or less at around 800 kilometers, while with introduction of the constellation, the crowded regions will move toward the one of the constellation. This can be seen also in terms of share of the indexes. So if we collect all the index for rocket bodies, inactive payloads and active payloads, at the beginning, we will have that the rocket bodies have the higher share, despite they have the less in terms of numbers of objects. While at the end of the deployment of our constellation, we will have that the constellation will have a share which will be higher than the sum of active and inactive payloads. So this was just to show that it is important to assess the impact of this new type of architecture, also to have, let's say, sustainable evolution of our space environment. In the future, we will do some more computation by changing the location of our constellation, but also by placing more than one large constellation, also to understand how they interact between each other. So to conclude, we have to think of our space environment, as I said before, like a resource that has a finite capacity. So we have to manage our, let's say, this space environment in such a way that it will be also for future mission, it will be sustainable in a long, let's say, time span. So with this, I conclude. But before leaving the floor for the questions, I would just have a small advertisement that we are organizing a capacity and space sustainability workshop also in Politecnico di Milano, and it will be held between 5th and the 8th June. It will be just 2 days. We are still defining the final dates. So if you are interested, I can send you an email if you give me. So thank you.